This is the design given to us. The design consists of a DDR controller which is attached to DDR SDRAMs. So DDR controller has an FML interface, a CSR bus, and a DDR interface. CSR interface is used to configure. CSR's FML interface is used to read or write anything on DDR RAM via DDR controller, and DDR interface is used to connect controller with DDR RAM. The more explanation on this design can be found in the provided documents of design. This is an overall block diagram. Here we can see that there are clocks and reset signal. Here we have CSR interface. This is our FML interface, and here this is our DDR interface. So how are we doing the verification? So as we can see in the test bench architecture, our verification strategy states that we have instantiated our design and we have connected to DDR SDRAMs via DDR interface. The CSR and FML interface are controlled via UVM verification IP, and there is an separate logic for clock and reset in our test bench top. Here you can see our test bench top. Here we have clock and reset signals, and we are driving the clock and reset signals from logic here. Further, here we have our DUT instantiated as mentioned here. The DDR interface is connected via DDR interface, and then the DDR interface is connected to SDRAMs. Here we have FML and CSR interface also DUT also connected to respective interfaces. Then we are passing interface to our UVM library via config db. So moving on to the UVM, these are our interfaces. We have CSR interface, which consists of address, write enable, read enable, and data in, data out bits. We have FML interface, where we have address, strobe, write enable, acknowledge, select, and data in, data out. And here we have DDR interface. So this is an block diagram of our verification IP. The verification IP consists of CSR and FML interfaces that are passed via our test bench top. See, the interfaces are passed to verification IP via test bench top, and we are passing the interfaces here. So the interfaces are then connected to drivers and monitors. The driver drives the interface. Both CSR and FML driver and CSR monitor and FML monitor monitors the interface. Here is another sequencer that is used to drive a sequence over to driver. So this is our UVM sequence item. The UVM sequence item consists of address, write data, write enable, read enable, and read data. So here is a constraint which states that the write enable and read enable cannot be high at the same time. This is to avoid racing conditions. Moving on, these are our sequences. We have CSR write sequence, CSR read sequence, and then FML write sequence and FML read sequence. Both of these sequences get us a certain address and certain data, and perform respective operations via driver. So in CSR write sequence, we can say that address and data are taken from user, and then write enable turns 1 and it is then passed to the driver. Similarly, in CSR read sequence, we have same address and read data is then one is turned 1 and it is passed to the driver. This is our agent. As you know, the UVM agent consists of sequencer, monitor, sequencer, driver. So we have here driver and sequencer, and then the driver is connected to the sequencer via sequence item port in both CFML and CSR agents. Here is our environment. In our environment, both our CSR agent and FFML agents are instantiated and are built, so we can use them. So here is our driver. The driver consists of for CSR driver consists of CSR write and CSR write and CSR read tasks, which are performed via sequence with respect to sequence item passed. So same in FML, it consists of FML write and FML read tasks, and with these tasks are occurred according to the CSL read and write sequence. So we are using makefile. The makefile can be seen here. The makefile has following commands: make, compile, make tool, and make sim. So if you want to compile and run test yourself, you can use make, compile, and make sim mentioned here. This is the output waveform. In our test, we are performing two basic operations, which is first we are writing some data to address 0 and then address 20, and then after that we are reading that data. As we can know that FML interface consists of 4 burst transactions. So in each write and read we are writing 4 burst, 4 double words, and then we are reading 4 double words. Here you can see that at here in yeah, as you can see that in FML interface the address is 0 and data we are writing is first double word, second double word, third double word, and fourth double word. This is the data being written. How we can show that data is being written? Because we can say that see that the write enable here is 1. So after writing this data, now see when we read the data, what should we get? So here we are reading the data. How we are reading the data? You can see the address is 0 and write enable is also 0. So you can see that we are getting same double word 1, 2, 3, 4, same 4 double words, same as what we wrote there. You can compare them. And similarly here we are writing to address 20 and we are reading from address 20. Here also we are getting same data on upon read and write, so we can say that our design is fully working properly. Moving on to the design compiler. Here is the area that comes out using design compiler. The area total comes out to be 1154.6. Moving on, for time analysis we use prime time. So in prime time the setup slack come to be 3.78 and hold slack come out to be 0.21. In PD, this is our obtained physical design, and the chip area report is here. Here we can see the total area is this, total capacity area is this, and area of cells is this. The power report is